Hello, everyone. So thanks for coming to this candidate talk of Naman Agarwal. So Naman is a grad student, a fourth-year grad student from Princeton University, supervised by Elad Hazan. So he uses optimization algorithms to solve both convex and non-convex machine learning tasks. So in this talk, he's going to use some of his new second-order techniques for machine learning. Okay.
Thanks everyone for the introduction, and thanks everyone for coming. I'm going to talk about second-order methods for machine learning, and this is going to be based on three works. The work LISA, which was with Brian Bullins and my advisor Elad Hazan. The work FastQubic, which was with Zewa, Brian Bullins, Elad, and Tengyu Ma, again at Princeton. And then the third part's also based on some leverage score sampling work that I did with Shyam Kakade, Rahul Kidambi, who's a student, Yin Tatley, Praneeth Netrapali, and Aaron Sitford. So let me just dive right into it. So I'm just going to straight away define the problem of supervised learning. I'm assuming a lot of us have seen this before, but let's just set the baseline correctly. So you're given a labeled data set, so essentially m examples, and each example is essentially a tuple of xi, which is the training data, and yi, which is the label. Okay. Once we've got this data set, we select a parameterized model, f sub theta of x. So theta is our parameters, and f sub theta of x is a function that maps x to the label y. And most parameterized machine learning gets captured by this kind of setting. And some of the considerations that you want to have while selecting your parameterized models are things like whether the model is expressive enough, whether it generalizes or unseen data, and how well we can optimize on our model. Okay, so once you've chosen a parameterized family and a data set, now you try and solve the ARM problem, which is basically defined as follows. So you pick a penalty function L, which has two arguments. One is going to be the label that you predict, and the other one is going to be the true label, and it gives a score of how bad your prediction is with respect to the true label. And then you sum it over all examples, and you minimize this function over theta, which is the space of parameters that you're searching over. Okay, so so essentially the aim is to minimize this function f of theta, and this model captures things like linear regression, logistic regression, SVMs, neural networks, and things like that. In the first part of the talk, I'm going to make some assumptions. So in the first part, I'm going to focus on these things which are called generalized linear models. So here, the parameterized family is assumed to be a linear predictor. So essentially, your prediction is going to be theta transpose times xi. Your loss function is assumed to be convex in theta. And in addition, we add a regularizer, which is an L2 norm square regularizer. This kind of regularizer is usually added for ensuring generalization, and it also has the added benefit of providing curvature for optimization. Okay. This restriction, yes.
So in what sense it's generalized? Isn't it like your linear model?
No. So,
you call them GLM.
They call generalized linear models because you still capture things like logistic regression on top of it. So essentially this loss function here is general. It's not necessarily just ridge regression. So it could be logistic function on top of it. That's why they're called generalized. Okay. Yeah, so this captures things like ridge regression, logistic regression. So this is going to be the first part of the talk. So while dealing with this, we are going to think about M, which is the size of the training data set, and D, which is the dimensionality in which theta lives in. Both of these things to be extremely large. Think of it of the order of tens of millions, maybe hundreds of millions. And the other consideration that we're going to have is that the data could be sparse. So when I say the data could be sparse, these examples X size could have very few non-zeros. Even if they live in high dimensions, they could have very few non-zeros. So that's a consideration that we're going to have all throughout. Since I have the function written up here, let me just go ahead and make some definitions. Some additional structure that we're going to impose on top of the ones that we've done is smoothness. So smoothness says that the second derivative of the loss function with respect to theta is always bounded by L times identity. So L is the smoothness parameter. This is a slightly more restrictive definition where I've assumed this over all examples, but I'm doing this for simplicity in the talk. And then secondly, let's define the condition number of the function, and the way I'm going to define it is just define it to be L over lambda. So often we've seen this to be the ratio of the smoothness over the strong convexity, where the strong convexity captures the curvature that you have in the function. And for simplicity, again, since we've added an L2 norm square regularizer multiplied with lambda, I'm just going to assume that that provides the sufficient curvature in the function. So L over lambda is going to be my condition number. So that's going to be the setup. Any questions for that? Yeah.
So for that, you need a lambda over 2, right, for the 2 norm.
Right, that's correct. So it should be, that's a good catch. So it should be lambda over 2.
And also for the L, you need the average over M, but over M.
So the way I'm defining this is that the average is implicit in the function, and this lambda is inside the. So think of this lambda, so this summation is over both of these quantities, and then the average sits out. In that case, the definition is correct.
I'm thinking if lambda theta square is outside of summation,
Then you'll have to put an average
you
there.
have a 1
Yes,
time scale.
yes, correct. But yeah, in this, I should have put a bracket more correctly here. Think of the bracket here. Okay. Right. Okay, so let me just give a quick overview of what I'm going to speak about. So essentially the key question that we're going to focus on is, can we leverage second order information efficiently in the design of optimization algorithms? Let me go ahead and say what efficiently means. So every time I'm going to talk about efficiency, I'm going to look for algorithms that are linear time in the ambient dimension. And in particular, I'm also going to focus on trying to leverage sparsity of the data as much as possible. If possible, we're going to look to improve upon what's known for first order methods, and both in settings where the function is going to be convex as well as non-convex. So just to give a brief outline, I'm going to start with just giving a very quick refresher on what's known for first order optimization. This is not going to be a complete story, but this is just to set the baselines correctly. After that, I'm going to describe an algorithm which we have called LISA, which stands for linear time second order stochastic algorithm. After that, I'm going to describe a non-convex algorithm called fast-cubic, which is going to give provably better solutions as well as faster running time than gradient descent on non-convex problems. When I say non-convex problems, we're going to focus specifically on things like deep learning. And why we're going to do that is going to get clearer in the talk as I go on. Okay? Okay. So as I said, let me just start off with a quick refresher on local search methods for optimization. The canonical method that I'm going to start with is something that we've all come to know very well now. So it's the algorithm called gradient descent. Remember, the goal is basically to minimize this function that's written up on top. And what essentially at a point theta t minus 1, what we do is basically take the gradient of the function with respect to theta t minus 1 and scale it with some parameter eta and take a step in that direction. Okay? So here's a little cartoon on how gradient descent might evolve on a convex function. If you want to see it as a local search method, basically what we're doing is essentially constructing a linear approximation of the function around the point theta t minus 1 and regularizing it with an L2 norm penalty scaled by 1 over 2 eta for it to not step out. So this essentially controls how far we are willing to trust our gradient approximation of the function. Okay. And just to remind people, in the case when the function is well conditioned, so let's assume kappa as a constant, then what we can basically show is that in every step we reduce the relative multiplicative error by a constant factor. So in t steps we get convergence that scales as something like e to the minus o of t. Okay. So that's gradient descent. Let's remember how much time it takes to compute the gradient in the ERM setting. So essentially it takes roughly O of md time per step. M, remember, is the number of training examples, and d is the underlying dimension. So you go over all the examples and then you compute the gradient with respect to each of those examples. Remember, this again can leverage sparsity. So if your data is sparse, this is going to be m times s, where s is the sparsity of the data. Okay? So that's gradient descent. Let's talk about another alternative where you basically replace the gradient step by an unbiased estimator of it. So essentially nabla tilde of f, which is an unbiased estimator. Here on the right you have something on a convex function, it kind of bounces around a little bit, but on average it converges. And what you get essentially in convergence is that you lose out on the linear convergence guarantee that you had, so the multiplicative per step guarantee that we have, but we still get convergence that looks like something of the order of t to the minus half. Of course, it is affected by the variance of the estimator that you have in your gradient. Okay? So these are the two canonical methods, gradient descent, stochastic gradient descent. And then, I should have mentioned, so why is stochastic gradient descent sometimes preferred in practice? Because now making a step is extremely simple. So instead of iterating over all of the examples, you can just sample one random example from your ERM problem and then take the gradient with respect to that. You can also do a small mini batch and things like that. So let me just quickly remind people of how the landscape here looks like. So again, so we are considering smooth and strongly convex functions which have condition number kappa. For gradient descent to converge to an error of epsilon to a relative error of epsilon, we have a running time that looks like md times kappa. So kappa times log 1 over epsilon is the number of iterations of gradient descent that's required, and md is the time that it takes to compute each iteration. An improvement that was proposed a while back, I think in 1983 by Nesterov, is the idea of accelerated gradient descent, which uses the idea of momentum. And what you do here is that you reduce your number of iterations from kappa log 1 over epsilon to something like square root of kappa log 1 over epsilon. And a paper by Nemirovsky and Yudin also showed that if you just have access to a gradient oracle, then this is in fact the tightest thing you can hope for. Essentially, square root kappa log 1 over epsilon is the iteration complexity that you must pay for if you just have access to a gradient oracle. Okay, so that's the story with respect to gradient descent. Remember that we also have access to a stochastic gradient oracle in the case of ERM and things like that. And another idea in this space which came much more recently is the idea of variance reduction, where you basically merge these two things together, gradient descent as well as stochastic gradient descent. And the idea here is that you take one gradient step, which is reflected by MD, and then you take kappa many stochastic gradient descent steps, and together this will count for one step of the algorithm, and you can show that the error decreases by a constant factor in each step. So you get a running time that looks like MD plus kappa D log 1 over epsilon. Okay. And then further work showed that you can actually merge the second, and you can combine the second and the third approaches. So sort of you can add acceleration on top of variance reduction to get a running time that replaces this kappa here by something like square root of kappa m. You can see that this running time here is always going to be smaller than the running time on top. This is always true. It's only an improvement. It's only an improvement if kappa is large, but this is at least always less than up to less than this quantity up to constant factors. This rate was also shown to be tight by a recent paper by Arjavani and Shamir and Woodworth and Srebro. Essentially, the idea is that if you've got access to a gradient oracle and access to a stochastic gradient oracle, essentially something like the ERM setting, then this is the best you can hope for. So a natural question to ask here is that is this sort of the limit of what we can hope to do with respect to gradient and stochastic gradient based algorithms? Okay. So that's the story with respect to first order optimization. I'm going to change gears now and talk a little bit about second order optimization. And just to remind people, again, something that we've seen multiple times, let's remember a very canonical second order method called Newton's method. And the idea here is that to take the curvature of the function into account as well. So far we've only taken the first derivative into account, but let's start taking the second derivative into account as well. And the idea here is that we want to minimize this local approximation of the function at every step. So this is essentially the second order Taylor approximation of a function at the point theta t minus 1. Okay, and you take the second order local approximation and you minimize it per step and you take a step with respect to that. Okay, so if we know that this the function is convex, in which case or strictly convex, in which case this is strictly is a positive definite matrix, then you get a step that looks something like this. Essentially, you take a gradient step, but you scale it with respect to the inverse of the Hessian. Okay, so this can be seen to be the minimizer of the quadratic that is written on top. Okay. So just to give a cartoon, this basically, suppose you've got a convex function, you take a quadratic approximation at the point theta 1, you move to its minimizer, and you repeat. Okay. Let's talk about how the convergence of Newton's method looks like. And here basically, this analysis is very classical. Essentially, you get a two-phase convergence. There's a phase 1 where you cannot take full Newton step, but you have to dampen the Newton step, and this roughly takes O of 1 many rounds. And after constantly many rounds, you can get into this phase where no more damping is required, and you sort of get rapid quadratic convergence. So you get convergence that's of the order of log 1 over epsilon. So basically that's saying that you need to take a total of log 1 over epsilon steps before you can get epsilon relative error. Okay? So essentially looking at this analysis, it tells us that all of the time that's spent in second order methods is essentially spent in computing the Newton step. Once you're able to compute the Newton step, this analysis tells us that this is already enough. You can sort of, because you're getting factors like log, you can hope to ignore. So it's only going to be a few Newton steps before you can converge to the optimum.
Can you describe in more detail the algorithmic difference between phase 1 and phase 2? What do I compute?
Oh yeah, so the algorithmic difference between phase 1 and phase 2 is that here, so remember, the Newton step here was unscaled. I did not put any scale on top of it. When I'm not close enough to the optimum, this turns out to be a bad strategy. You have to scale the step, so scale it down a little bit. And as you get close, so that represents this damping that I said in phase 1. So you have to dampen the step, don't take full Newton steps. And in phase 2, once you're close enough to the optimum, it's enough to not dampen the Newton step and take full Newton steps and continue.
Do you know how close I am?
This closeness is actually very clearly defined, and in things like, so for certain functions you've got something called the Newton potential, and if the Newton potential is small enough, you can check the Newton potential. If the Newton potential is small enough, it tells you that damping is no longer required.
But in the O of 1, you are hiding some parameters of the function.
Yes, so that's a good question. So there is a class of functions called self-concordant functions where this is not required. This is actually O of 1. But if you've got generally just smooth and strongly convex functions, then indeed this can be something like kappa. And the way you would implement it in practice is actually not to do Newton steps at the start of the optimization. So essentially maybe you want to do a first order method at the start of the optimization to get close enough. And then after that you can then start to leverage things like Newton method.
Then you need to have convergence guarantees in terms of the Newton decrement rather than the function value.
No, so no, you could actually, so you in smooth and strongly convex cases, you can actually get guarantee with respect to just how close your function is with respect to the optimum. So if the distance with respect to the optimum is less than some function of say the condition number, then you can, yeah. Right. So the Newton decrement thing is for self-concordant functions. For general smooth and strongly convex functions, like something like 1 over kappa or something suffices.
Acceleration. Can you?
You can still apply. You can still
Will
apply.
you get something in terms of the distance to her, not just the function value?
Oh, so if indeed you also know that, so suppose you also know that you didn't start too far away. So suppose like you have some bound on the diameter of how far you are from the original, then up to kappa everything's going to look the same, right? Because again, distances and function values can be exchanged up to kappa again, so remember the reason I'm happily doing that is because that kappa is going to show up in the logarithm always, because we are only looking for error guarantees of linear convergence. So it's okay to sort of push out, that kappa that shows up in the logarithm. So, okay. Any more questions? Right, so time is essentially spent in implementing this step. So let's go and look at how to implement the step. So remember, the step looks like something like this. Essentially, it's the Hessian inverse times the gradient. And essentially what Newton's method is doing is reducing a convex optimization to essentially linear system solves. Okay? And if we do it very, very naively for things like ERM, essentially you've got to have a running time which looks something like this, md square plus d to the omega. So md square is required just to construct the Hessian. Remember, the Hessian is a d by d object and you've got to iterate over m examples. So just to construct the Hessian, it takes md square time, and then d to the omega, however low we can hope to push the omega. Omega is the constant, the best constant that we know how to invert d by d matrices. So this will be the running time of a naive implementation of Newton's method. And this is, of course, extremely prohibitive. So again, if you think of m and d of the order of tens of millions, this is going to be extremely high. The other aspect here is going to be this d to the omega is still going to suffer with respect to the sparsity. So even that the examples are going to sparse once you sum them are going to be sparse once you sum them up, there's no guarantee of sparsity of this Hessian matrix. Okay. So, this brings up some natural questions. A natural question here is that are there algorithms that can perform this computation in linear time? So when I say linear time, again, I mean linear in the dimension and possibly be able to leverage sparsity. And secondly, can we make use of the stochastic structure that we are given due to ERM? Again, very similar to the way we did it in the case of stochastic gradient descent. Just to see here, as in the case of stochastic gradient descent, we do have an unbiased estimator of our Hessian. So just pick an example, take the Hessian of the loss function with respect to that, and that gives you the Hessian, an unbiased estimator for the Hessian. So like SGD, we have an unbiased estimator of the Hessian. So the question is, can we leverage this to sort of compute this step more efficiently? Before I describe our algorithm, let me just quickly, and this is going to be a very, very incomplete list of some of the previous attempts. So one beautiful line of work here is the work of Spielman and Teng, which basically provide algorithms for solving diagonally dominant linear systems. So diagonally dominant essentially means that linear systems in which the matrix comes from a graph Laplacian. And this has been improved significantly over the last few years. The problem is that these necessarily do not apply to the settings that we are interested in, things like linear regression, because diagonal dominance is a property that might not hold. Okay? So that's one of the works that I wanted to highlight with respect to linear time.
Would it hold if you increase sufficiently this lambda parameter or something? Because it feels that it should affect diagonal of the...
Yes, so it would. Of course, if you take lambda to be extremely high, this is going to be diagonally. But then lambda is typically, you should think of lambda as something like 1 over m and things. It's a really small quantity, actually. Okay. Again, so there's a huge line of work in this area. I'm just going to mention another one of them, which was a work by Erdogdu and Montanari, which is called NewSAM. And essentially the idea here is to take the Newton step as follows. So you've got an unbiased estimator of your Hessian, take a large batch with respect to that, do some sort of a low rank approximation if needed, and invert that matrix, and then take your step with respect to that. Okay? As stated in the paper, the implementation time of this method still scales as something like omega of d square. I can go into detail later if required. But one of the other issues with this is that taking the inverse sort of breaks this nice unbiased property that we have had with respect to gradient descent steps. So even if I have an unbiased estimator of the Hessian, taking its inverse and sort of taking the expectation of that, unfortunately no longer matches the inverse of the Hessian.
Sorry, I'm confused by the previous thing you said. So you said now that lambda is not a constant, it's 1 over m?
Lambda should really be thought of as something like 1 over m, yeah.
But kappa is a constant?
No. So kappa, I didn't want to think of kappa as a constant. I'm going to give all my running times depending upon kappa. I'm not going to hide kappa in my running times.
You were thinking of kappa as a constant, right?
No, that was just for one slide there because I didn't want to write the e to the minus o of t. So everywhere else, we're going to specifically say here is my dependence on kappa, and we should not really think of kappa as a constant in our algorithms.
But then you said that O of 1 in the delta.
Yeah, that's a good question. So the O of 1 here, this O of 1 here, so I should have probably said O sub of kappa. So the O of 1 actually holds for things like self-concordant functions. These are very special cases of functions. Then you get this O of 1. Otherwise, this will be something that depends upon, that depends upon something like kappa. But the way we would actually implement it in practice is to run a first order method that gets close enough, and that close enough sort of depends upon kappa, but the running time of that first order method to get to that level of accuracy depends something like logarithmic in kappa.
And therefore logarithmic in m?
And therefore logarithmic in m.
So is kappa constant for self-concordant functions or not necessarily?
Kappa as defined is not a constant for self-concordant functions. They could have unbounded kappa. So kappa is not what's constant. You sort of get a local definition of kappa. So essentially what you can, like if you look at any point, if you sort of look at the region that's around that point, just build a small ellipsoid around that point, in that region kappa looks roughly constant. But globally kappa might not look constant. Okay. Okay, so let me jump into the first part of the results that I'm going to show in the first part. So first I'm going to define a recipe to construct an unbiased estimator of the Newton direction. So we saw that sort of inversion of a large batch Hessian does not respect this unbiasedness property. So the first thing I'm going to show is how we can construct an algorithm that creates an unbiased estimator of the Newton direction. Then I'm going to show that each of these iterations are going to be implemented in time that scales as O of D. Again, linear in the dimension, and it's also going to scale as linear in the input sparsity. So that's going to be a desideratum that we had at the start and we're going to satisfy. Again, we're going to have convergence that's going to scale as something like log 1 over epsilon, so linear convergence. I'm going to show some, we implemented this method and sort of compared it to some standard first order methods. I'm going to show that so the better should be maybe taken with a pinch of salt, but it converges always almost as good as first order methods and sometimes better. And this I will not be able to talk about much, but I'm happy to go into detail. But now if you take some of these ideas and sort of couple it with these fast matrix sampling techniques, you can even beat what's known for accelerated methods. And I'm going to state this rate formally later, and I can describe it.
So basically the whole point of Newton method is completely killed, right? Because you don't have this quadratic convergence anymore.
That is not necessary. In some sense, this is a trade-off that you must pay. If you want to spend just linear time, then you should sort of not expect to get something like log 1 over epsilon. No, because again, so you could have things like diagonal dominance, and then that's definitely not the case. So it's not provable. But I do think that this is the case. So somehow. The way you should probably take these methods is that, can we still do something? So it could still be the case, as we actually observe in practice, that using second order information efficiently gives you better convergence in terms of like what happens in practice. In terms of actually what you can show in theory, it's going to be very similar to what we get for first order methods. So this is not going to be necessarily an improvement in theory over first order methods, but it turns out to do well in practice. Here I'm going to state some other work that I have which actually shows an improvement over what can be done by first order methods. Okay. Okay, so let me just start off giving the recipe for creating an unbiased estimator of the inverse. And remember, what do we have? So we have access to these unbiased estimators of the Hessian, and we want to come up with an estimator for the inverse of the Hessian. And the idea is going to be the following. We're going to use a very popular, well-known series for the inverse, which is called the Neumann series. So essentially, given any matrix A that lies between 0 and identity, the inverse of the matrix can essentially be represented as this infinite series, right? We know this very well for scalars, but it also holds for matrices. Once you've got this series, here's going to be the strategy. Pick a probability distribution P over non-negative integers. So essentially think of it as picking a probability distribution over all of these terms. So P0 to P infinity, where summation of Pi is going to be equal to 1. From this probability distribution, sample an integer I, right? And once you've got this integer I, we're going to essentially build an estimator for the ith term, okay? So we're going to build an estimator which looks like of the ith term, which essentially looks like something like this: identity minus Hessian to the power I, right? So I'm going to now describe how to build this unbiased estimator for this term Ti. So essentially, this is an iterated product. Let's take I unbiased independent estimates of the Hessian that I had. So remember so I have access to these estimators. I'm going to sample them I times independently, okay? And what I'm going to do is essentially just in this iterated product, just replace each instance of this Hessian by an unbiased estimate that I just sampled, okay? Now it's not going to be so hard to see. Essentially, since these estimates that I took were independent, expectation just filters in through the product, and what you get is that the expectation of Ti tilde is equal to Ti, okay? Any questions regarding this? So once you've got an unbiased estimator of Ti tilde, you can now happily see how to convert it into an unbiased estimator of the inverse. Essentially, you just rescale by the probability of picking the term I, right? So this is going to be my final estimator, Ti tilde over Pi. And if I take the expectation over the probability of choosing I get that this is exactly equal to summation of Ti, which is the inverse of the.
So the variance would depend both on this distribution P and on like specifics of your function.
The variance of this estimator, yes, exactly. But the way we're going to think about it, since I'm assuming that the Hessian is kind of bounded between 0 and identity, the real thing it's going to depend upon is essentially how this probability distribution is chosen.
I see. So somehow you can have like pessimistic variance bound for this Ti tilde, which is like okay, just assuming that A is sandwiched between 0 and I.
Yes, so you can have what I'm going to show is what is going to be, it's essentially the variance of this estimator. I'm going to precisely tell you that, but it is going to, as you said, it is going to of course depend upon how you choose this probability distribution. Okay, so that's basically that's the way to construct a recipe to construct the unbiased estimator of the inverse, given access to unbiased estimators of the Hessian. A question to ask here is that okay, so far I've just told you how to construct these things. But again, if I'm dealing with these as matrices, then I'm still spending d square time, right? Because I'm still sort of multiplying out matrices together, and this is not, I don't want to spend d square time. So now I'm going to describe how you can use this recipe to construct. So remember, all I did was just construct an unbiased estimator of the Hessian inverse. Now what I'm going to tell you is how we can actually use this to construct an unbiased estimator of the Newton direction. Right? So remember what the Newton direction looked like. So essentially what we can do is take a full gradient of the function at the point theta and multiply it with the Ti tilde that I constructed before. Remember, this is still going to be an unbiased estimator of the Newton direction, because the expectation of Ti tilde over Pi is, you'll have to scale this by Pi. This is the inverse of the Hessian. So this is going to be an unbiased estimator of the Newton direction. Okay? So if we expand this product out, this looks like the following. The way I constructed Ti tilde was essentially a product of this form, and then you're trying to multiply this gradient term here. Okay. So essentially, as long as we can perform this computation efficiently, I have computed an unbiased estimator of my Newton direction. And the way we're going to do it is essentially, if you look at this product very carefully, you can see that what this reduces to is essentially being able to compute the following thing efficiently. Given any vector v, if I can multiply it with the matrix which is an estimate efficiently, then I can iterate that over this product. So if I have an oracle that computes this guy for every v, then I can sort of iterate this over this product and sort of I times and get an efficient algorithm to compute this guy. Okay. So we can sort of now define this as a primitive. So this primitive is often called stochastic Hessian vector product oracles. So the idea is that given any vector v and at a point theta, as long as I can come up with an estimator w tilde whose expectation is this quantity here, nabla square f of theta times v, then I can actually go ahead and use this oracle I times to sort of compute an unbiased estimator of my Newton direction. Okay. Any questions regarding this construction? Okay.
Is that an estimate of the Hessian inverse?
So Ti tilde is an estimator of the Hessian inverse.
Can you go back to one slide?
One slide, sure. Yeah.
Yeah, that one.
Yeah. So Ti tilde over Pi is my Hessian estimator, inverse estimator.
Okay, divided by, okay.
Yeah. So you have to rescale. I removed it for brevity in the next talk because that's just a scalar, so you can always rescale. Okay. So a good question to ask is, when is this primitive efficient? And so far, everything that I've said has not used the assumption that I had made about over generalized linear models. And here is where I'm going to use that assumption. So essentially, if you look at generalized linear models, you've got a loss function that looks like theta transpose xi comma yi. And let's take the Hessian of this loss function with respect to theta. And if you look at it carefully, what you get is that this Hessian is going to look like a scalar function, L double prime, multiplied with xi transpose. So essentially what you get is that the Hessians are rank 1 matrices. And now this is easy to see that if given a vector, I can easily multiply the Hessian of Hessian over a single example efficiently. When I say efficiently, this is going to be in time that's going to be, again, proportional to the sparsity of the input, because again, look, I'm multiplying xi with a vector v, so it's going to scale as the sparsity of the input. So therefore, this primitive can be implemented in time that scales as the sparsity of the input, which in particular implies that this guy here, I can compute in time that's proportional to I times the input sparsity, right? So the I that I have sampled here times the input sparsity is going to be the running time to compute that step. Okay. Now let me go ahead and describe the algorithm once. So what I'm going to do is essentially pick two parameters, which are going to be this parameter p, that's just the probability distribution, and a parameter s. And the way the algorithm is going to look like is going to be the following: you iteratively do compute the gradient of the function at theta. For from I going from 1 to s, you're going to compute multiple Newton estimators. This is going to be to kill the variance, because as you pointed out, the variance could potentially be large, and the way we're going to do it is just by averaging many estimators. So let's compute this quantity wi, which is going to be the inverse, this estimator that I had mentioned how to compute. And then at the end, we're going to sort of average these estimators that we've computed and take a step in the above direction. When I say above direction, I mean w hat. Okay, so that's going to be the overall algorithm. Let's look at the running time for this guy. So essentially, computing the gradient takes time that's proportional to O of md. Let's look at what happens to this loop here. You're going to run the loop s times, so that's going to come up. You're going to get a term that's going to be essentially an expectation that looks like what is the I that you're going to sample in expectation times d, right? And all of these d's, you can think of them, these d's are replaceable by input sparsity always. Okay, so that's going to be the running time of the algorithm. And that sort of gives me the theorem which says the following. So essentially, Lisa returns a point in the parameter space theta t. In total time, that scales to something like log 1 over epsilon d times m plus O of kappa times s. So I'm not going to show the derivation of this very carefully, but the way when we are selecting these distributions, the way to select them turns out to be such that this expectation here should be something like kappa. So a good distribution to think about is something like a distribution over integers that goes up to roughly kappa terms. Say you could roughly think of them as being uniform. So uniform over the first kappa terms, and sort of just dies down very quickly after that. Yeah.
I'm a little bit confused about the notation here. So, I mean, are there two different I's going on? One is a random variable.
Oh yeah, you're right. You're right. So this should have been a j.
So, and all these other I's are also J's, or are
no.
I's?
So let me say. So this is j, and this is j, and this is j. So everything here should think of it as j.
Everything's J.
Everything here is j. This is a different I. This is the I that. So I mean, this is still okay because I'm sort of like this is just a term by itself, right? This expectation of I being sampled from the probability distribution of I. So I mean, this can hold by itself by not relating to that I.
Okay.
Yeah.
It sounds like you're not going to show us the variance calculation.
Yeah, I'm not going to show the variance calculation because I sort of want to tell different things, but I'm going to still mention what is the bound on the variance that we can get.
Great.
Yeah. So let me first point out that this is going to be linear in sparsity. And this term S is essentially this term, how much you're going to oversample is going to look like the variance. And the best bound that we can show in theory on this variance is actually pretty large. It scales as something like kappa square. So, so this S, in theory, the best bound we can prove is that this should scale as kappa square. What's interesting, and something that I still don't have a proof for, is that in practice, we never actually need to set this S to be anything larger than 1. So this method converges even when you set S to be equal to 1, and it turns out to be perfectly fine. But yes, the best bound we can in theory that we can show is something like kappa square.
S equal to 1, you just only do one.
Yes, S equal to 1, you literally just take one estimator and move in that step.
But then the complexity will be what's the sample complex for taking this? Ask me the hashing inverse.
Right, so that's kappa, right? So this expectation here is kappa.
Okay, that's kappa.
Right. Oh, your question. Okay, so your question is how this estimator here.
Yeah.
In practice, this is a very, very small batch. So this estimator here is the Hessian estimators are like small batches of like 20 or 30 or something. So the Hessian estimators themselves are tiny. And actually, if I remember correctly, it even converges by taking even if you take one or two and have like each Hessian estimator, even if it's on one or two examples, it still converges. Okay.
In that case, then if you see 20 or 30, then that means the complexity, computation complexity step is same or roughly the same order as the limited memory Gaussian-Newton. Is that true?
Okay, so it's a little bit different. So okay, that's a good question. So I think here is the thing. So what do you define as a step, right? So if you define this entire thing as a step, then essentially I'm taking still kappa many of these estimators, right? So I'm taking kappa. So in that sense, it's still larger. Like this step here is still larger than quasi-Newton. Okay. So that's it. That's the algorithm. So let me just put it in context of what we know for first order optimization, because that's what I wanted to compare this with. So essentially LISA sort of fits somewhere here. You've got a running time that looks like MD plus kappa times S times D. As I said, this S in practice is of the order of 1. So then the best running time in theory sort of gets comparable to things like SVRG and Saga. But in theory, the best we can still show is that this is still of the order of kappa cube. So in theory, this is going to be slower than SVRG and Saga, but in practice, this turns out to be comparable, and I'm going to show curves next. Okay. Another work that I will not have time to talk about is going to be this extension of LISA that we have, which basically improves over accelerated methods. And here, the idea is going to be that if you use second order like methods, you can replace the m that appears here in the rate of accelerated methods by something like d. So if you want an intuition about this, what's really happening here is that essentially even if you've got a quadratic which has, so think of just linear regression. If you've got a linear regression, if you've got essentially a matrix which is a sum of m rank 1 matrices, what you could do is, if you subsample correctly and sort of scale these vectors correctly, you can reduce it, you can get a constant spectral approximation of that matrix by just sampling essentially d many of those rank 1 matrices. So this comes from matrix Chernoff bound, and essentially that's why this m here essentially gets replaced by the dimension.
Wait, why do you need LISA actually? Why can't you just do sketching and then apply accelerated SVRG?
That's a good point. So here you could do something like that. The problem with sketching is that this D here unfortunately may be bad with respect to sparsity. So the output of sketching might not be sparse. So you really have to do this leverage score sampling kind of thing. So essentially here what we actually do is something very similar to that. So you do essentially sample with leverage scores, which actually takes original samples from the input examples. That preserves sparsity with respect to input examples. And then you sort of run something like an accelerator.
Wait, so the difference between the method we described is literally that you sample this, how to call it, rank 1 Hessians with some weight.
Mm-hmm. Okay. So yeah, so this is an improvement over the best known for things like accelerated SVRG in cases when m is much larger than d. And if you look at some of the standard data sets which we use, this actually happens for something like 80% of the data sets on this. The other justification of this idea is that if you actually look at statistically what the sample complexity should look like, so suppose you're solving linear regression, and what should m be as compared to d, and it turns out that m is something like sigma squared d over epsilon, where sigma is the noise that you have in the statistical case. So in that case also you see that m is actually larger than d.
And then, if you run this one in practice, is it faster? Then, for example, is the LISA++ better than the LISA?
Actually, it's interesting. So I don't actually recommend LISA. Like we've had some implementations of this, but this algorithm here is fairly complicated. LISA turns out to have an algorithm that's good, like 4 lines of code. This one here actually has multiple subroutines, because you're sort of having some subroutine to compute leverage scores, which also takes time like this. So essentially, I don't have a practical implementation of this algorithm yet. So I can't say that in practice this performs better. This running time is actually in theory. So it's an improvement in theory.
So I have another question about the theory. So even for LISA, right? So these stochastic techniques, you will pay something for bias and you will pay something for variance. And what you decided is you want to have no bias at all, and you pay everything in the variance.
Variance, yes.
So is the reason to believe that that's the optimal choice? I mean, could there be a better trade-off between bias and variance that allows for a little bit of bias?
That's a good question. That comes in basically in the choice of the probability distribution that I pick.
You're unbiased for any probability.
That's true. Okay, so
I'm saying some other
some other
have a little bit of bias, but maybe much less variance, and perhaps overall a win.
so it could. So actually, what I didn't describe carefully is there's another estimator that we come up with, and in that case, actually, we do get some bias, and I can describe that in person a little bit more. Another way to sort of induce bias in this. Yeah, let me actually tell you. So another way to sort of induce bias would be to sort of put zero probability in the tail. So just literally just sample from the first kappa many elements. So say, sorry. Yeah, so sample like with a probability distribution that has support only on the first kappa elements, right? And actually that turns out to do slightly better in practice. So it does pay to get some bias in practice. Okay, any other questions?
Yeah, actually one more. So since like you can get rid of the parameter s in the Lisa++, can you use some of the ideas to get rid of that?
Yes. So yes, that you can do. So essentially, what I didn't say here is that you can actually get a running time like this by essentially what you could do is use SVRG to essentially solve each of these linear systems by itself. So you could always just use SVRG to solve the linear system by itself, right? That will be something like, that will be like biased sampling essentially, because you're using some sub-solver to solve a Newton system. That's not going to be, correct in expectation. So that's going to be slightly biased. So you can use an idea like this to sort of put it under this. The reason I prefer Lisa is that it's still kind of, why would you want to do SVRG necessarily on each of the subsystems as compared to doing it on the entire function?
Yeah, it defeats the purpose.
It defeats the purpose in some sense. Okay, so let me just make a remark here. There's a recent paper by Arjavani and Shamir that shows that essentially in the model that we usually compute, that is just sampling uniformly when we want a stochastic gradient oracle, in that model, getting a runtime better than this is in fact impossible. And to get to a runtime that scales as something like square root kappa d, you actually have to have access to sampling non-uniformly. And this is something that we can sort of leverage in the case of second order methods. Okay. Just giving some performance plots here. So essentially I've just compared Lisa to things like SVRG and Saga. And this is what we get in some of the popular data sets like Mushrooms, MNIST, and CoverType.
And you didn't compare to LBFGS?
That's there in the paper. In the talk I removed those things just because I wanted to say that, okay, it does better than first order methods. But in the original paper, actually it's interesting. LBFGS actually does quite well in these settings. So LBFGS, if you've got sort of regularization that's on the higher side, then LBFGS is not that comparable. But as your regularization gets lower and lower, LBFGS actually sort of squishes in somewhere here as well.
Or it's not further way below?
No, it's not way below. It's actually not way below. It's actually quite squished somewhere here. Okay. Okay, I guess I'm sort of running out majorly on time. Let me say something about non-convex functions. I'll try and go through it as quickly as possible. So, okay, so we're going to remove some of the assumptions that we had. So in particular, we're going to make the assumption, now remove the assumption that this L is convex. So L can be non-convex, and we still are going to hold on to the assumption of smoothness, but that's all we're going to say, because there's no meaning of strong convexity anymore now, because the function itself is non-convex. But smoothness is something that we're still going to hold, and this model still continues to capture things like deep learning, essentially. Okay. So now we're in the domain of non-convex optimization. In this case, it's easy to show that global optimization is NP-hard. In particular, even being able to decide whether you're at a local minimum or not is NP-hard. So just this decision problem that you're at a local minimum is NP-hard. So then, of course, we cannot hope to get this log 1 over epsilon type of guarantees that we had before. So what can we hope to do? Well, even though this is hard, we've seen that sort of deep learning and other applications like matrix sensing and factorization and some rank-constrained STPs have been extremely successful in the case of non-convex optimization. And sort of if we cannot get to global optimization, let's try and hope for something weaker. And one of the things that we can hope for is something like a first order local minimum. Essentially, this gives us a locally and local efficiently computable certificate of optimality, which just says that, okay, just tell me whether the gradient of the point, gradient at this point is 0 or not. This is satisfied by all global minimum, but not every point that satisfies this is a global minimum. In optimization, often we sort of relax this and ask for a weaker guarantee, which is like whether the norm of the gradient is small. And this can be achieved by things like gradient descent or stochastic gradient descent. But just being able to say whether the gradient is small or not does not let us sort of distinguish between these two cases. So on the left, you've got something like a saddle point. Here, the gradient is still 0. Here also the gradient is 0, but clearly there's a local direction of decrease in this left case, but whereas there's no local direction for decrease in the right case. Okay. There's been sort of many papers that have sort of tried to say that, okay, maybe saddle points are problematic, and some of these papers kind of make toy models of deep learning and say that essentially saddle points are abundant in higher regimes for these toy models. So if you look at the landscape of optimization in the regions where there is high error, these saddle points tend to be sort of proliferated in those regions. Another sort of experiment by a group in by Yoshua Bengio's group is they came up with a heuristic second order algorithm, and they sort of compared near a saddle point how SGD behaves as compared to their sort of heuristic second order algorithm. So SGD is something like this here, and the second order method kind of just gets through the saddle point quickly. On the other hand, sort of our local good question, another question to ask is that, are there cases where local minima are good enough? And indeed, there's been sort of multiple examples of this shown. So for things like matrix completion and factorization, tensor decomposition, some toy models of very popular networks called residual networks, and some rank constrained SDPs. Essentially here what's been shown is that local minima are essentially as good as essentially global minima. So for all of these papers, essentially what they show is that getting to a local minimum is good enough for optimization.
Residual networks, it's very toy.
Sorry?
It's a very toy model, right?
It's a very, very toy model of residual networks, yeah.
It's a linear is it?
Yeah.
Yes, it's a linear residual network, correct. Okay, yes, so one quick way to sort of distinguish between these things is to, if you have this kind of situation happening, so on your left you've got, if you look at this lowest eigenvalue of the Hessian, it's going to tell you necessarily that that's negative, and clearly there's a negative direction for decrease. On the right hand side, you're going to have that the function really looks convex around that point locally. So all the eigenvalues are going to look positive. Okay, so we can use sort of second order information to get to to distinguish between these points, which seem hard to distinguish using only gradient information. I put a star there because of course because there's been recent work showing that this statement is not necessarily fully true. Okay. So we can ask for a better baseline, which is basically baking this requirement into the desideratum. So that's going to be epsilon delta approximate second order local minimum. So that says that, okay, at a point where the norm of the gradient is small, less than equal to epsilon, but additionally you also want that the Hessian of the function should be minus delta times identity. So the lowest eigenvalue of the Hessian should be larger than minus delta. Okay? So as epsilon and delta go to 0, and these points sort of approach local minimum. But indeed, even if epsilon and delta are both 0, this does not necessarily still guarantee me local minima. But often it turns out, for the examples that I had mentioned, this is still good enough because they tend to have these strict saddles where saddle points tend to have either a curved up situation or a strictly curved down situation. Okay, so the question here is, can we use second order information efficiently to ensure the above convergence to these kinds of points? And in this work, joint work with Zewon, we answer the question in the positive, and we get another sort of benefit, which is that we actually, while designing the algorithm here, we converge to points that look like this faster than what gradient descent can guarantee you to even a point that looks just like the first condition there. Okay, so let me just state what the landscape here looks like. So for gradient descent, to converge to a point where the norm of the gradient is less than equal to epsilon, it takes time that's roughly proportional to 1 over epsilon square. This is the number of iterations that you have to do, and each iteration takes time roughly m times d. So this is the running time for gradient descent. If you do the standard vanilla stochastic gradient descent, then you get a convergence that's something of the order of 1 over epsilon to the 4. If the numbers look a bit off, remember on the right hand side I have norm of gradient and not norm of gradient square. That's how we are usually used to looking at these numbers. So in the non-convex world I prefer norm of gradient, so I have stated it in that regard. So you get a running time of this, and what we show in this paper Fast Cubic is that we can get to points where the norm of the gradient is smaller than epsilon and Hessian is larger than minus square root of epsilon in time that scales as something like md over epsilon to the 1.75. So this is a strict improvement over over things like gradient descent. And if epsilon is going to be small, then this is a strict improvement over what's known for stochastic gradient as well. Let me also say that since the publishing of this paper, there's been a very active work in this area, many of them by Zewan, sort of improve. And so for the conditions that I've stated here, as far as I know, this is still the best running time known, but sort of some of these conditions can be relaxed, some of the oracle models can be relaxed and things like that.
So like basically, as you defined it with like epsilon and delta, what would be the dependence on delta, for example?
That's a good question. So this question has been later answered by Zewan. So in the paper we actually prove it only for epsilon and square root of epsilon. It turns out
kind of weird. So you would want I don't know. It's like it doesn't type check, but okay, I guess there is some.
No, actually, okay, that's a good question. The reason it doesn't type check is that here there's also a smoothness constant that's hidden. So think of this as omega sub L. So to actually get to type check this correctly in terms of the if you just measure it with respect to the dimensions, just to see whether it type checks correctly, there should also be a smoothness constant hidden here. But I mean,
so in follow-up works.
No, so in follow-up works this has been made to delta, and there's a clear sort of a clear graph of how this scales with respect to epsilon and delta. Okay. Okay, so again, let me just quickly, let me skip this for a moment here. So the reason I skip this is I want to state the theorem just because the time is over. This is the theorem that we get, the final theorem with respect to fast cubic. If we have more time, I can go ahead and now describe how the algorithm looks like. Okay. So, oh shoot, this doesn't go back. Okay. Okay, so here is where we were. So we wanted to use second order methods. So let's look at how we can design a non-convex Newton's method. And the way we're going to do it is, okay, let's try this standard Newton step. But of course, it's immediate to see that this is a bad idea. Just take a concave function and try and do Newton's step with regard to that. And you can see that it actually moves you in the opposite direction. It moves you towards the direction of the maxima instead of decreasing the function. So this is a bad idea. And of course, this is a bad idea because the way we actually defined this step here was to look at this quadratic and take the minimizer with respect to this quadratic. But this is a minimizer only when this matrix here is positive definite, but which is not the case for non-convex functions. So clearly, in any such setting, the infimum of this quadratic is going to lie at infinity, and you don't want to move to such points. So in this paper, we use this idea of cubic regularization that was proposed by Nesterov and Polyak in 2005. And the idea is to look at the third order Taylor expansion around the point theta t minus 1. So you take all the three terms in the expansion. And now we want to sort of bound this term. So we want to put an upper bound on this guy here. And the way we do it is to make this assumption that the third derivative of the function is bounded always by this operator norm by this quantity m. This also means, read another way, this also means, and which is actually a weaker but sufficient condition, is going to be that the Hessian of the function is Lipschitz. So Hessian is Lipschitz with respect to the L2 norm by a factor of m. Okay. So what this does is that this lets us sort of replace our step by solving this cubic that you have here. So essentially, I replace the third order term by this m times a cubic, m times L2 norm cube. Okay, and now this gives us at least a meta algorithm which looks like the following. You've got a function s. You take you are at a point theta 1. You build a cubic approximation, and you can actually show under this assumption that this remains an upper bound on the original function. So you build a cubic approximation of the function, you minimize it, and you continue. Okay, so this is the idea of cubic regularization. And what Nesterov and Polyak showed was that if you do this epsilon to the 3/2 many times, then you can converge to a point that's an epsilon comma square root epsilon approximate local minimum. This was the result of Nesterov and Polyak. But what Nesterov and Polyak didn't provide was how to actually solve this cubic. Right?
So your work is could be seen as a stochastic version of that, pretty much.
It's not. Yeah, you can see it as a stochastic version of that. It's not necessarily a stochastic version of that. I'm going to, but it's hard to say what.
In terms of epsilon, they kind of got the right thing.
In terms of epsilon, they got the right thing. What we do is basically figure out how to implement this step, still running every time in linear time with respect to the data. Okay. So, they did have an algorithm in their original paper, but that was basically scaling as something like md square plus d to the omega. And what we show basically is the following. So the algorithm which we propose is you repeat the same procedure, roughly epsilon to the 3/2 many times. And each time you're going to solve your subcubic to high enough accuracy. I'm not going to describe high enough because that's going to be a little bit technical. But what we show in a lemma is to get high enough basically just means that it should be of accuracy enough such that if I repeat the procedure epsilon to the 3/2 times, I still maintain the guarantee that exact minimization would have gotten. And to get this high enough accuracy, we show that this minimization can be implemented in time that's md over epsilon to the 0.25. Okay? So this gives you the epsilon to the 3/2 multiplied with md over epsilon to the 0.25 and giving you a rate that looks like md over epsilon to the 1.75. Okay? So that's going to be the main result. Okay, any questions regarding this? And I can go ahead and now describe how this comes about. Okay, so one of the other things that is, so we don't want to, okay, but I can stop here depending on the interest. Sorry?
Do you have a conclusion?
Yeah, sure. So let me, wasn't able to get through this, but okay, so yeah, so just to summarize, what I was able to, this was the question that we started off with. Can we leverage second order information efficiently in the design of optimization algorithms? We looked at it in two cases. One was the convex case in which we proposed this algorithm, LISA, that ran in linear in the data representation. It performed better than first order methods empirically. And what I didn't show but I can describe later is that it can also be leveraged to show the best known running times in the case when epsilon is greater than, examples is greater than dimension. In the non-convex case, I just was able to describe an algorithm, fast cubic, which avoids saddle points. It converges to approximate local minimum, and it runs in time that's faster than gradient descent. Okay. Thanks.